When poets and storytellers speak of the ocean, they are often struck by its constant, restless motion. From the rolling deep of the open sea to the crashing coastal surf, even the most casual observer is impressed by the swirl of tides or the march of waves against the shore. But few note the silent, subtle passage of currents. Yet the power of currents to move and control the seas is unmatched. Currents are cohesive streams of seawater that circulate through the oceans. Some are short-lived and small, while others are vast flows that take centuries to complete a circuit of the globe. The Gulf Stream current, which shows up in this temperature-coded satellite image as a broad, dark orange swath, has followed this course through the North Atlantic for millennia. In contrast, the small eddy currents that spin off the Gulf Stream die out within a few months. Currents are caused by winds, gravity, and variations in water density in different parts of the ocean. There are two distinct current systems in the oceans: surface circulation, which stirs a relatively thin upper layer of the sea, and deep circulation, which sweeps along the deep sea floor. The dominant pattern of surface circulation is the gyre, a well-organized, roughly circular flow. 5 enormous gyres spin in subtropical waters, 2 in both the Atlantic and Pacific Oceans, and 1 in the Indian Ocean. Smaller polar gyres stir the northern Atlantic and Pacific. 1 surface current circles endlessly around Antarctica. These gyres are made up of currents set in motion by winds and gravity, and steered by the placement of the continents and the rotation of the Earth. Wind is the most important cause of surface currents. When strong, sustained winds blow across the sea, friction drags a thin layer of water into motion. The movement of the very topmost layer of the sea pulls on the water just beneath, which then in turn starts the layer under it moving. Energy from the wind is quickly dissipated, so wind-driven currents slow down with depth and finally die out within a few hundred meters of the surface. Surface currents are also triggered by gravity. The top of the sea is not flat. It has broad hills and valleys. Where currents converge or run into a continent, water piles up. The major ocean gyres circle around a low mound a meter or so high, and in summer, intense sunlight can heat and expand seawater, raising the surface by several centimeters in the tropics. Currents run down these gentle slopes under the pull of gravity. Winds and gravity start water moving, but the currents that form don't flow parallel to the wind or straight down the steepest surface. Instead, the currents move at an angle to the force that generates them, a phenomenon called the Coriolis effect. The Coriolis effect occurs because the Earth's surface rotates faster at the equator than at the poles. It influences the paths of moving objects that are only loosely in contact with the ground, from currents to winds to airplanes. When objects move toward higher, slower-moving latitudes, they outpace the rotation of the surface and seem to veer toward the east. If this plane left Miami heading straight at Chicago, it would miss its target unless it corrects for the Coriolis effect. When objects move toward lower, faster-moving latitudes, they lag behind the rotation of the surface. This plane from Valparaiso veers toward the west and misses its destination of Santa Cruz by not adjusting for the Coriolis effect. The Coriolis deflection is to the right in the northern hemisphere and to the left in the southern hemisphere. The movements of currents are also constrained by the shape of the ocean basins. When a current runs into a continent, it must turn aside. The complex interplay between wind, gravity, Coriolis effect, and topography determines the location, size, shape, and direction of the surface current gyres. For example, consider this North Atlantic gyre. Like all the subtropical gyres, It is triggered by two of Earth's prevailing winds, the trade winds and the westerlies. The trade winds start a current that is turned by the Coriolis effect into a westward flow along the equator. The equatorial current gets warmer and warmer as it travels across the tropics. On the other side of the gyre, winds known as the westerlies, combined with the Coriolis deflection, push mid-latitude water to the east. Called the North Atlantic Current, this flow loses heat to the atmosphere. The eastern and western currents of the gyre begin where the equatorial and mid-latitude currents are blocked by land. On the Atlantic's western boundary, the Gulf Stream moves away from the equator and flows north. The Gulf Stream is the strongest, deepest, and fastest part of the gyre, and it transports an enormous amount of heat toward the poles. Finally, the slow and very shallow Canary Current runs south along the eastern edge of the Atlantic, carrying cold water to the equator to complete the gyre. A single trip around this circuit takes about 10 years. Although the gyres dominate, a number of other currents also make important contributions to surface circulation. For example, the very warm equatorial countercurrent, which flows eastward, can help trigger the unusual weather pattern called El Niño. A much colder flow, called the Labrador Current, travels along the west side of Greenland. This current is notorious for flushing icebergs, including the one that sank the Titanic, into the heavily traveled North Atlantic shipping lanes. Many surface currents, the ones with names, have been in constant motion for millennia. Other currents are temporary. Longshore, rip, and upwelling currents only run in certain seasons or weather conditions. Longshore currents flow along coastlines when waves run into the shore at an angle. They bulldoze great volumes of sand along the shore, causing beaches to disappear and harbors to fill in. Rip currents form where obstacles channel water away from the shoreline. Many an unwary swimmer and beachcomber has been swept out to sea after stumbling into a rip. Upwelling occurs when winds push surface water away from the shore, and deeper water rises to fill the gap. These cold currents bring nutrients to the surface and stimulate high plant and animal productivity. Deep water circulation has a scale, pace, and power very different from surface circulation. Deep currents twist together into a continuous stream that loops through all the oceans, called the global conveyor belt. With a volume more than 16 times the combined flow of all the world's rivers, the conveyor belt slowly but steadily empties one ocean into another, and over the course of 1,000 years, turns the water in them upside down. This vast global circulation is driven by density variations in the ocean, sometimes called thermohaline circulation because it depends on temperature and salinity. The conveyor begins on the surface of the sea, near the poles. There, the water gets very cold, chilled by low air temperatures to freezing and below. Polar seawater also gets saltier, because when sea ice forms, the salt is left behind. As seawater gets colder and saltier, its density increases, and it starts to sink toward the bottom. Surface water is pulled in to replace the sinking water, and in its turn eventually becomes cold and salty enough to sink. Thus a current begins. The conveyor belt begins at the surface of the North Atlantic, where great amounts of water cool and sink off the coast of Greenland. Hemmed in by the continents, this new deep water can only flow south, past the equator, all the way to the far ends of Africa and South America. As the current travels around the edge of Antarctica, fresh streams of cold water sink into and recharge the conveyor belt. Two sections split off and turn northward, one into the Indian Ocean, the other into the Pacific. Both these currents warm up and become less and less dense as they travel, enough that they eventually rise back toward the surface. Drawn by the inexorable pull of the conveyor belt, these now warm waters loop back the way they came, and eventually return to the North Atlantic, to begin the long journey all over again.